Welcome to the lesson on gravitational potential energy. Gravitational potential energy, this falls in with the discussion about energy we had in a previous video. We said energy can either be kinetic or potential or another form. And gravitational potential energy is a type of potential energy. It's given by the symbol UG, and the units are in joules. The easiest way of describing gravitational potential energy just to someone who has never encountered it before is this. It tells you, if you know the mass of an object and how high it is, it tells you how much energy that object will have when it hits the ground after you drop it. So with that simple explanation in mind, let's look at a few examples. I have two blocks of equal weight. We'll say they're both 2 kilograms. The first block here, we'll say, is 10 meters off the ground, and the second block here is 5 meters off the ground. If these two blocks were allowed to drop, let's calculate how much energy they'd have once they reach the bottom. Now remember, our work equation was work equals force times distance. And so if the force of gravity acts this way, and the block is also dropping in this direction, we can figure out the change in energy of the block from that force times distance formula here. So the work on this block would be force is equal to mg, which is 2 times 10, and the distance is 10 meters drop. That comes to 200 joules of energy if this block, starting at rest, were allowed to drop to the ground to here. Now we'll look at this block here. So that's work on block 1. And we'll look at the work on block 2. That's equal to force times distance. Now the force on block 2 is actually the same. It's mg, which is 20 newtons. So that's 2 times 10. But the distance in this case is not 10, but 5 meters. So the total work is 20 times 5, 100 joules. So this block will have 100 joules of kinetic energy once it hits the ground there. Notice the general formula for the work that's being done on this block before it hits the ground is mg, which is the weight force, times height, the height it started at. So that's mgh. And this is actually the formula for our gravitational potential energy, mgh. Let's take a look at an example of the way that gravitational potential energy, when it is being reduced, is being transformed into another type of energy like kinetic energy. And the example you often see in an exam is the frictionless roller coaster. So I have a roller coaster that starts off at the 50 meter mark in height, drops down to the ground, and then rises again to this point here, the 30 meter mark. And I have a cart on this roller coaster of mass 100 kilograms. Let's figure out the gravitational potential energy at 3 points on this roller coaster. So we'll start up here. UG equals mgh, which equals 100 times 10 times 50, which equals 50,000 joules. At the bottom here, UG equals mgh. Since h equals 0, the gravitational potential energy also equals 0. And over here on the right, UG equals mgh equals 100 times 10 times 30, which equals 30,000. So say this roller coaster had a cart which started from rest, V equals 0. And then it had just a little nudge over the edge there, and then it slid down to this point here. The thing we need to understand is that any gravitational potential energy lost leads to an increase in kinetic energy. And this is best summed up by this little equation I'll put down. The gravitational energy plus the kinetic energy in a frictionless roller coaster has to equal a constant number. In this case here, if V equals 0 up here, kinetic energy equals 0, therefore UG plus EK equals 50,000 plus 0, so that equals 50,000 joules. And this equation here is true for every instant on this roller coaster. So we can use it to find the kinetic energy both here and here, which are unknowns to us right now. So let's look at this point here. We'll call this point B and this point C. So point B, UG plus EK equals 50,000. The energy is conserved. The UG in this case is 0, so 0 plus EK equals 50,000 joules. That indicates that the kinetic energy equals 50,000 joules. And the kinetic energy has to equal a half mv squared. So 50,000, which is the kinetic energy, has to equal a half times 100 times v squared. 100,000 equals 100 v squared. 1,000 equals v squared. Well, this is a bit tricky. Square root of 1,000. I think v equals, what is this, 31.6. I'm just going to say v equals around 30 meters per second, but certainly this is the kinetic energy at this point here. So let's figure out the kinetic energy at this point here at C. At C, the same equation holds. UG plus EK equals 50,000, but UG here is 30,000. So 30,000 plus EK equals 50,000. Therefore, EK equals 20,000, and that has to equal a half mv squared. So we have 40,000, multiplying both sides by 2, 40,000 over m, which is 100, equals v squared. 400 equals v squared, that's nicer. 20 equals v. So the velocity here is 20. And it is only at this velocity that the kinetic energy comes out as 20,000, which enables us to conserve the total energy, 50,000 joules. This problem gets a little trickier when the car starts in motion. So let's look at the figures that occur if that happens. Okay, so I redraw the roller coaster. So height here is 50, height here is 0, height here is 30. And the roller coaster goes through, we'll say A, B, and C. But the roller coaster in this case starts off with, what can we say, 10 meters a second. It still weighs 100 kilograms, and it'll still drop 50 meters. So we worked out before the gravitational potential energy at point A was equal to 50,000. That doesn't change. The gravitational potential energy at B was equal to 0, and the gravitational potential energy at C was equal to 30,000. So even though the cart is in motion at all these times, the gravitational potential energy formula doesn't include velocity. So we don't have to worry about that in terms of the potential energy, only for the kinetic energy. So now we ask ourselves the trickier question: what is the kinetic energy at A? Well, EK is equal to a half mv squared, which is a half 100 10 squared, which is equal to, what's this? 5,000 joules. So, we said before, gravitational potential plus kinetic energy must be a constant. In this case here, kinetic is 5,000, gravitational is 50,000, so UG plus EK is equal to 5,000 plus 50,000, it equals 55,000 in this case here. And since energy must be conserved, that is the same total energy that you will find at B and C. So we'll put that down a little neater down here. UG plus EK has to equal 55,000. So the next challenge is to work out what is the velocity at B. What do we know? I'll move it over here. At B, EK plus UG has to equal 55,000, just as it did at point A. 55,000. So EK plus 0 has to equal 55,000. Therefore EK equals 55,000, which equals a half m, which is 100, v squared. And if you solve this, you get v is equal to 33.2 meters per second, which is faster than the original answer we found, even though my original answer was approximation. If you found the exact answer yourself, this speed would be faster than that because the cart starts with some energy. So now let's find the velocity at C. We know that at C, EK plus UG must equal 55,000. EK is the mystery, but we know UG, that's 30,000. 55,000. So taking 30,000 from both sides, EK is equal to 25,000. This must also be equal to a half 100 v squared, which equals 50,000 equals 100 v squared. Therefore 500 equals 50,000 equals v squared, and v is equal to 22.4 meters per second. This is the only velocity that would allow us to conserve the energy, because this is the velocity that gives you 25,000 joules worth of kinetic energy, and if you add those joules of kinetic energy to our gravitational potential, you'll find you have the same energy as you started with down here. So the things to remember is that the gravitational potential energy formula is UG equals mgh. It basically tells you how much energy is available to something at a certain height, and the total energy is conserved in the universe. So that if something is moving down in height under the force of gravity, there must be some other form of energy which the gravitational potential energy is being transformed into.